The problem shown here has the objective to calculate the natural frequencies and then compare with them with the exact frequencies of this bar, which is fixed at one end and free at the other. What they have done is they have divided the bar into two elements and then they have calculated the frequencies numerically. So we'll be verifying that using Abaqus, and these are the material properties: Young modulus and the density, and the cross-sectional area is 13 to 10 raised to minus 6, while the length is length seems to be missing. It is 1 meter. So yeah, we'll move on to Abaqus. So when you open the Abaqus, it looks like this, and we'll start with the standard expressive model. First, we'll change the work directory to a location where it is easily accessible. FPA project. Okay, and then we'll save it as third problem frequency. So we'll start from the part making. Click on this part and we'll go with the 2D planar and wire, and our approximate size will be 2. 2 because this is something that one should decide on their own, and the length is 1 meter, so to properly fit into the view I'll take it as 2 and continue. Now we'll sketch a line of 1, not to say any dimension unit, but 1 comma 0, and click enter. That's it. So this is a line of 1 meter. Next we move on to property modules. Click on the materials. We'll name it as math 1. First, in general, we'll click on density and assign the density of 7800. Right. Then in mechanical, we'll do elasticity elastic, and young modulus as 2 into 10 raised to 11. So 2. Poisson ratio 0.3. It's not mentioned, but we'll go with 0.3. Before that, let me delete this hyperelastic. Yeah. Okay. Next, we need to here we'll go with this option of create profile, and we'll go with generalize. Nothing has been mentioned, so we'll go with generalize and assign the area as given 330e minus 6, and we'll do I11, I012 as 0, I22 as 1. So these are moment of inertia of the object about this axis, like x, y, and then x, y, 0. Okay. Then that is the section defined. We'll create here beam, and we'll go with beam. Yeah, we'll assign the material here 1. We'll just we'll profile 1. Before analysis we'll specify the material density again. 17, temperature is 25, and material name is mat1. Section's Poisson ratio is 0.3. Right, and that's it. Okay, and then we'll assign the section. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . section has been set. That is it. In this assembly, this is a, we will do independent mesh here. Click on OK. Then in interaction, nothing to be done. In step, we'll create a step. Here, instead of general, we'll go linear perturbation, frequency, and continue. Here we are interested in 2 frequencies, but we'll go up to 5. And just click OK. And done. Next step is loading. So we need to create a boundary condition of fixed joint. Fixed boundary condition, right? So we create, continue, select this point, and do end cast ray. Okay. Next is meshing. In meshing, here what you'll find is, if the finer mesh we do, the closer the results come to the one we'll see, the one that is mentioned in the solution. So we'll go with 2 first and see the results. Number of elements as 2, and then the element type. Something important here. Our element family is beam here. Okay. Okay. And then we'll just mesh it. 2 elements have been generated. That's good. Next is job creation. We will create job. We'll name it as frequency. Continue. Now by doing data check, we'll look for any errors. So assign beam orientation, it's shown. So again, we'll go to the assembly properties and then do this orientation stuff. Click on the line, just go with the default and click OK. So that error won't pop up now. So again, we do data check. Yeah. So it has been submitted for analysis, completed successfully, and completed successfully. Now submit it. So yeah, this analysis is running, and we'll see the results in time now. Okay, completed successfully. Now we'll go to results. Again, we can see the contour plot here, but we'll go to result and step frame and see the frequencies here. So these are the values that should match up with our answer of direct method, I mean exact difference. So these are the solutions that we are looking for, right? So we'll see that answers are somewhat close, like focus on the mode 3 and mode 5. Do not focus on even modes. 1, 2, 3, 3.6 and 2, 9, 7, 8.3. They're somewhat close, right? But still not exact. So what I'll go to mesh. So we'll see how finer meshes creates better results. We'll increase this to 20. And then we'll see how the results are changing. So now there are 20 elements. Again, we'll go to job, submit it directly, no need to data checking, and then we'll see the results. Yeah, this will take a little bit longer time because much more finer meshing. And go to the results. So yeah, I think it has been 1265. See, before it was a larger difference, but it has improved so much. 1265.9, 1265.6. Why we are not focusing on even modes is, you'll see from this solution itself, the values they have taken is odd. So yeah, we'll focus on the odd. So 3789.0, 3797 point. Again, the finer we go, the closer we'll get to the real solution. That is one thing. And then we can increase the number of frequencies, and we'll see that 5 and 6 are same, and then some odd and even are same. So but we need to focus on the odd only. So that's all for the solution.